right, so I'd like to welcome everybody to week 13, class number 1. What we're going to be doing today is we're going to be taking our final look at chapter 9, conceptual knowledge. This time we're going to focus on a really important and innovative idea in terms of how our knowledge is represented, which is connectionist networks. So this is a very powerful tool that is fueling the recent increases and advances in artificial intelligence. So we're going to take a look at what it means for human cognition, and then we're also going to take a look at how just the basics of connectionist networks operate so that we can understand how our minds might operate, and also how artificial intelligence is making the massive gains that it's been making in the last decade or so. So that's going to be part 1 of today's class, and then part 2 is going to be our look at language. So we are going to take a look at language. We're only going to stay a brief time on language, but it is an important part of cognitive psychology. It is one of the things that humans are very good at compared to other cognitive entities, other animals, for example. So we are going to spend a little bit of time on language, basically taking an overview of some of the issues and some of the challenges in understanding how we produce this very, very complicated verbal behavior. So we're going to get to that in part 2. In part 1, we're going to, again, as I said, talk about connectionist networks as a way of representing our knowledge. So this is going to be day 3, class number 3 of this face-to-face shutdown. So thank you once again for coming here and joining me today. And let's dive in with connectionist networks. So previously, when we were talking about conceptual knowledge, when we were talking about Collin and Loftus's spreading activation model, we were actually talking about this kind of connectionist network. So the connectionist network we're going to take a look at today, the nuts and bolts that we're going to take a look at today, would be the basic framework that would underlie something like Collin and Loftus's spreading activation model. And we're also going to see that this is the cognitive architecture that is underlying a lot of the advancements in artificial intelligence. So self-driving cars, the ability to recognize information and then act on information was very difficult to program using traditional artificial intelligence approaches, but connectionist networks have made it possible to create self-driving cars, and we'll see exactly how these complex behaviors are possible. Facial recognition programs are all based on, again, these ideas of connectionist networks, and also known as parallel processing networks. And we're going to see that we have been sort of dancing around and encountering connectionist networks throughout this our time here in cognitive psychology. So one of our first connectionist networks that we encountered went all the way back to when it was the first week when we were taking a look at representations, and we were looking at how letters are recognized. So this template model is not a connectionist network, but this pandemonium model with the feature demons and the cognitive demons, that is a connectionist network. And we're going to see how these connectionist networks make cognition, very complicated cognition possible, make modeling cognition possible, and give us insights into how probably we accomplish these cognitive feats. So that's going to be in part 1. We're going to touch on language in part 2 in just a bit, but right now let's dive right in to connectionist networks. So this again is about knowledge representation. How do we represent the things that we know and the things that we can do in our mind? So in our representational level explanation, how do we represent this information? We'll take a look at connectionist networks, then the nuts and bolts of connectionist networks, the different types of inputs, connections, how they're updated and programmed. All of that today when we take a look at this very important topic in cognitive psychology. All right, so let's take a look at knowledge representation. So we're going to consider the exclusive disjunction. So that's just a fancy way of saying we're going to see how it is that we understand X or Y. So if you are given a statement such as, you must participate in research or write an essay to earn course credit, but you can't do both, that's the exclusive disjunction. So the exclusive disjunction is the exclusive use of or, and it's the or that we typically use in everyday language, where you can have this or you can have that, but you can't have both. So that's the exclusive disjunction. And if you read the statement, you must participate in research or write an essay to earn course credit, but you can't do both, and you understand what it is that you can do with that statement, you have that knowledge represented in your mind. So if you understand that you can either participate in research or you can write an essay, but you cannot do both, and that is the way that you earn course credit, if you understand that, that means that that knowledge is represented somewhere in your mind. And we're going to take a look at exactly how that knowledge might be represented. So we're going to start off with a non-connectionist form of this knowledge representation. So this is a propositional representation. So this is offered up in sort of contrast to what we're going to take a look at later. But just to kind of show you that different representations have different features, we're going to take a look at a propositional representation or a list representation. So if you know what to do and how to interpret the statement, you must participate in research or write an essay to earn course credit, but you can't do both. If you can interpret, you can do X or you can do Y, but you can't do both. One way that that knowledge might be represented in your mind is just a series of statements, a list of propositions, such as if there is no X and there is no Y, then the statement is false, which means that you are not participating in research or writing an essay. So you are not participating in research, you are not writing an essay, you will not get course credit. So that's what that false means. No X and no Y equals false. That means you're not participating in research and you're not writing an essay, you're not getting course credit. If X, then true, means that X occurs, so you are participating in research, and true means that you get course credit. If Y, then true, means that the Y portion is correct, means that you are writing an essay, and that leads to a true outcome, a true statement, you are earning course credit. And then the final version of this, the final combination, is if you have X and Y, then that leads to false. So if you are doing both, then you're violating the rule. You are not allowed to do that to earn course credit, and that's why that's false. So the way to interact with this conjunction, this exclusive disjunction statement, the way that you possibly understand how to navigate the different options for this, you must participate in research or write an essay to earn course credit, but you can't do both, is simply to have these four options available to you. That, you have a list of what happens if you don't do X and you don't do Y. What happens if you only do X? What happens if you only do Y? What happens if you do X and Y? And you just have a list and you go down the list in order to understand the different outcomes. So that's one way that this can be represented in your mind. But how can this be represented differently in your mind? That's what we're going to now turn to when we look at connectionist networks. Because you can represent this same information, but in a very different form in this connectionist network form. So this connectionist network, it's a model of how knowledge is represented. It's also known as parallel distributed processing model. And this goes back to the parallel processors that we talked about early in this course. So it's not a serial processor, it's a parallel processor. It's got multiple waves of processing all occurring at the same time. These connectionist networks are made up of units and connections. And these units and the links between them are what allow computer programs these days to do facial recognition. We're going to see a model that shows us how a computer can do number recognition. So this is a very degraded number 7, but we're going to see a program that can take this input and recognize it as a 7. Take in these pixels and stimuli as input and come out with the output that, yes, this is a number 7. And we're going to see that this has many features in common with the pandemonium model proposed back in 1959 that allowed this pandemonium model network to recognize letters, regardless of what font they might be in. So we're going to take a look at that and how you might be able to recognize a 7. And at first it's going to look rather complicated, but the basic principles of these connectionist models are actually quite straightforward. So let's take a look at the connectionist model that would be able to recognize this number as a 7 and would be able to recognize all the numbers, all the numerals from 0 to 9. So this is an image, a representation of that connectionist network. So let's zoom in on this network and so we can take a look at its little pieces. So this is the network, and you can see that there's a whole bunch of units. Those are the circles, and there's a whole bunch of connections. Those are the blue lines and the red lines, and that's what makes up your connectionist network. You have those units and you have those connections. So in a connectionist network, there are 3 main types of units. The first one is input units, and these are the units that are activated by the stimuli. This is where the information comes in. This is where the input comes in. So in this representation here, in this connectionist network, this first layer on the left here, this first layer right there, that is your input layer. And this input layer, it's abbreviated here so that we could fit it on the screen. But this actually has 784 inputs. And each of these inputs represents 1 pixel in the image that is being fed to this program. So the pixels in the image of that 7, it had 784 pixels in its image. And each of these pixels is designated an input unit. And if the pixel is on, that is, if the pixel is white, then the unit is activated. If the pixel is black, the unit is not activated. So that's how the information gets into the system. One nice way to think about this is this works very much like the retina in your eye. So you can think of each of these little input nodes, each of these input units, as a cone in your eye, an optical receiver in your eye that if the light hits it, it turns on. If the light misses it, it stays off. Same thing with these input units. If the pixel is white in the image, then the unit turns on. If the pixel is black, the unit remains off. So those are the input units. Those are the beginning of the connectionist network. The end of the connectionist network are the output units, and these communicate the information. So this is here in this representation, the input network, 784 input units. Your output network your output layer, your output units are these 10 units right here. And these 10 units are what communicate the information to the outside person. So this is, if we can call back to the physical symbol system hypothesis, these are the one of the criteria of the physical symbol system hypothesis, that you are linked to the external world by designation, which means that the stimulus can be designated or can be shown to the physical symbol system, and that's through the input units. And then we have interpretation, which is the output units. So these output units get activated, and then somebody can take a look at these output units and say, oh, based on these output units, the number that this program saw is, in this case, it would be a 5, because it's the output unit that is most activated. So that's the designation. That's how the information gets output. And then between the inputs and between the output units, we have the hidden units. And these hidden units are the ones that process the information. These hidden units are the ones that crunch the numbers. So these hidden units are the units in between the input and the output, and there can be multiple layers of these hidden units. In this case, we have 2 layers of hidden units. There's layer number 1, there's layer number 2. And all of these units, the input units, the hidden units, and the output units, they are connected to each other. Hence, connectionist network, right? They're connected. Let's call it connectionist. Seems the thing to do. All right, so we have these connections between the units. These are the links between the units. And the processing power of these connectionist networks comes from the fact that these links are differentially weighted. And what that means is that some nodes are very strongly linked to each other. Units are very strongly linked to each other. Other units are very weakly linked to each other. Some units are strongly positively linked. Other units are strongly negatively linked. So these are all differently weighted links between the units. So for example, here we have links between the input unit and the first hidden units right there. And as you can see, some of those units are blue. Those are positive units or excitatory positive links or excitatory links. Those are links that carry activation forward and increase the activation of the node they're connected to. The red links, on the other hand, those are inhibitory units. Those decrease the activation of the units that they're connected to. So you have links in blue that increase the activation of the unit they're connected to. You have links in red that decrease the activation of the units they're connected to. And then the last thing that's represented here is the strength of these connections, which is the thickness of the line. So the thicker the line, the stronger the effect of the connection. The thinner the line, the smaller the effect. So a very thick blue line leads to a large increase in activation for the unit that it's connected to. A very thin blue line leads to a small amount of activation for the unit that is connected to. So we have connections between the input units and the first hidden layer. We can have connections between the hidden layers as well. And then finally, we have connections between the hidden layers and the output units. And based on the fact that these are differentially weighted, based on the fact that they have differential strengths, and based on the fact that they have differential effects, either increasing excitation of a node or decreasing excitation of a unit. Now, I apologize, I use nodes and units kind of interchangeably. We're going to try to use units, but you can either increase the excitation of a unit, making it more likely to fire, making it more likely to send its information forward, or you can decrease the activation of a unit, making it less likely to fire, making it less likely to move its information forward. So now that we've described these connectionist networks, you can see how this is very similar to the neurons in your brain, where neurons are connected to other neurons and they release neurotransmitters that makes the neuron more likely to fire or makes the neuron less likely to fire. It's very similar to the way that our own brains are set up. All right, so that is the basic parts of the connectionist network. And what we're now going to do is we're going to step back a little bit from this massively complicated connectionist network. And we're going to take a look at a simpler connectionist network just to kind of show the parts and how this could possibly work. And we're going to take a look at a connectionist network that would be or might be the way that you represent that exclusive disjunction. So we've already went through how a list representation might be the way that your mind represents this exclusive disjunction. But how can this be represented differently in your mind? Well, it can be represented in a connectionist network. So let's take a look at that right now. So this is going to be a very simple connectionist network because to start off with, there's only two inputs. The two inputs that you feed into this system, that you feed into this program, is the input X and the input Y. So this network is connected to the external world by inputs that indicate whether you have X, did you participate in research, or whether you have Y, did you write an essay. So if you participated in research, the X input would be activated. If you wrote an essay, the Y input would be activated in this case. So those are the input units. That gets the information into the system. The next part of this is the hidden units. And in this case, we have two layers of hidden units. One has 3 units in it. The other one has only 1 unit in it. And then finally, we have the output, which is only, again, 2 possible outputs. Either the output is true, meaning that you followed the rules and you're going to earn course credit, or the output is false, meaning that you didn't follow the rules and you will not earn course credit. So the last thing we need to do is we need to connect all these units. So we get a connectionist network. So there are those connections there. And they need to be differentially weighted. So most of these have a weighting of +1. A few of them have negative weightings of -2 and -1. So we're going to put those negative weightings with dotted lines just so they kind of stand out a little bit. And then the last thing you'll notice is that some of these hidden networks have numbers in them. And the numbers in that some of these hidden units have numbers in them. And the numbers in the hidden units indicate the activation that that unit needs in order to fire. So this unit up here, it needs to have a total activation of 1 in order for it to turn on and send information to the next level. This unit down here has to have an activation of 2 in order for it to turn on and send its information down the network. And then the final thing that we will do here is we're going to start with most of the network turned off, except for that false output. And what this means is that if you don't have X or Y, you're starting with false right off the bat. So that's just the way that the network begins. This is the default setting when you don't have any X input and you don't have any Y. So let's start looking at what happens when you start inputting different pieces of information to this connectionist network. And let's see how it can understand, that is, give you the correct output for every single situation in that exclusive disjunction. All right, so let's start off with when you have X. So if you have X, if you participated in research, then we know that the conclusion should be true. That is, you're going to earn course credit. So does that come out in this connectionist network? If it does, when we give an input of X into this connectionist network, that is, we turn on that X input unit and it starts to propagate its information, it starts to propagate its activation, what should happen in the end is that the output unit should turn on the true output and it should turn off the false output. So let's see if that actually happens. So we send in the information. We say we have X. We've participated in research. That activates the X input. We don't have any Y. We didn't write an essay, so the Y input is left off. So the X input starts sending its activation down the connectionist network. So it sends 1 unit of activation to that center unit, that number 2 unit. It sends 1 unit of activation to that top unit. And because of this, the top unit has enough activation in order to turn on. It only needed 1 unit of activation in order to turn on. So it turns on. The middle unit there, that one right there, that required 2 units of activation. So it only got 1 unit of activation. So it's going to stay off. It is not going to turn on, and it's going to lay dormant. It's not going to send any more signals down the wire. So what happens now? Well, we have that top unit. It got activated. It will send its signal down to the next layer. So it sends a +1 activation down to the next unit. That unit requires 1 unit of activation in order to turn on. So it turns on as well. And then here's where we get our first taste of a negative activation. So because this unit turns on, it is positively linked to the true output unit. So it sends its activation down the link and turns on the true output unit. But notice also that it's connected to the false output unit. But importantly, it is negatively connected. It's got that -1 weight. What that means is that it sends -1 units of activation. And what that does is it turns off the false output. So we finally have an output here that indicates that if you have X, then this statement is true. That's exactly what we were looking for. So that indicates that this network is correct in this analysis. That if you have X, the statement will be true. If you participated in research, you will earn course credit. This network figured out that if you start with X, you're going to end up true. If you start with participating in research, you're going to end up earning course credit. All right, so that's if you have X. That's if you participate in research. Let's take a look at another possibility. Let's say that you have Y. You have written an essay. Once again, if I told you if you do research or write an essay, but you can't do both, and you say, oh, I've written an essay, you would expect that you're going to earn course credit. So the conclusion here should once again be true once we feed the information through the Connectionist network. If this Connectionist network represents how we think about X or Y, then when we put in an activation of Y, the output should be true. So let's take a look at what happens this time. So this time the Y input gets activated. The X input stays off. It stays dormant. Because the Y input gets activated, it sends 1 unit of activation to that center unit of 2. So once again, it sends 1 unit of activation here, but this unit requires 2 units of activation to turn on. So it's not turned on yet. It still stays off. It does not have the required amount of activation for it to turn on. But this other connection here, right down there to this unit, does turn that unit on, because that unit needs 1 unit of activation, 1 amount of activation. It received 1 amount of activation, so therefore it turns on. So now it sends its information down its link, and it sends 1 unit of activation down its link. That is linked up to this unit right here. That turns that unit on, and then that unit sends 1 piece of information, 1 positive piece of information down to the true output unit, turning it on. And then much like we saw before, it sends 1 negative piece of information down to the false unit, turning it off. So now what we've seen is that if you start with Y and no X, the conclusion that this network comes up with is that that's a true conclusion. That is, you're going to earn course credit. And we can see once again that this network is correct. All right, continuing on. Let's take a look if it can handle the case where you have X and Y, where you have done both. Now, bear with me on this. Remember that you can do one or you can do the other, but you can't do both. So you cannot do both. So in this case, we would want to see a conclusion of false because you have not followed the rules. You have not done this correctly. You have done this falsely, incorrectly. So what we would want to see here is that if we activate an X input and we activate a Y input, then the false output should remain on and the true output should never be turned on. So let's see if this network is able to create that output given the links that it has. All right, so let's take a look at this. We'll start off with the X input. That X input sets 1 unit of activation to this unit here, and that turns that unit on. It also sends 1 unit of activation to this center unit here. Whoops, jumped the gun. To the center unit here, and that does not turn this unit on because this unit requires 2 units of activation. But lo and behold, this is the first time that this unit is going to get activation from a second input unit, the Y input unit. And now we have 1 piece of information coming in from the X input, another piece of information coming in from the Y input. 1 plus 1 is 2. This unit here now finally has enough energy to activate. So it gets turned on. And then the Y input also sends 1 piece of activation down to this unit here, and it activates that unit as well. So now for the first time, we have all 3 of these units in the hidden first layer activated. So what is their sum total? What are they all going to do? Well, that top unit is going to send 1 piece of activation down to that second layer. This bottom unit is going to send 1 piece of activation up to the second layer. So right now we have 1 plus 1 equals 2 units of activation. That should be enough to turn this on. But wait, look what's happening with this unit right here. It is sending -2 amounts of activation. So it is turning off this particular unit here. So this unit gets 1 plus 1 amounts of activation, that's 2. And then it gets -2 parts of activation here. So the total activation, the sum of the activation here is 0. Because it's 0, that unit can't turn on because it needs one amount of information, 1 unit of information to turn on. So it doesn't turn on. It has nothing to send down to the output units. So the output units stay the way that they are. False stays on. True does not get turned on. And the network is correct because the network correctly, again, interpreted that if somebody says you can do X or you can do Y, but you can't do both, and you have done both, that statement is false. You did not follow those particular rules. All right, and lastly, suppose that you have no X and no Y. So you didn't do X, you didn't do Y. What we should find is that the conclusion should be false. You are not going to get any course credit. And in this case, this is the easiest one to analyze because there's no input into X, there's no input into Y, nothing gets activated, the network stays the way that it is, and the default for this network is false. So in this case, once again, the network is correct as well. So we can see that the network, this connectionist network with its connections between input, hidden, and output units, correctly interpreted and correctly represented the knowledge of how to deal with X or Y. So you might be representing this exclusive disjunction X or Y and your understanding of it as a list representation, but it is also quite possible that you are representing it as a network, as a connectionist network, and that's how you understand how to deal with X or Y. That's why when somebody says you can participate in research or you can write an essay to earn course credit, but you can't do both, that's why you can understand that particular statement and know how to proceed, because theoretically you have this connectionist network somewhere in your mind representing that knowledge of how to deal with that or statement. All right, so that was a very simple connectionist model to kind of illustrate the basic principles. Now we're going to take a look at the power of these connectionist models, and we're going to take a slightly more complex connectionist model, which this is from your textbooks for your knowledge of living things. And once again, it is quite possible that everything we know about living things, everything we know about animals and plants and other forms of life, we have in a list representation. So everything that we know about canaries, maybe they're represented in a list in our mind that canaries can grow, canaries can move, canaries can fly, canaries can sing. Maybe that's all that we have is just a list of these representations, a list of these propositions. And the same thing for robins. Robins can grow, robins can move, robins can do all these other things. So that might be the case. We might just have a list of propositions in our mind. On the other hand, we might have a connectionist network. So this is going to be a very simplified version of the network that we would require in order to represent this. We're going to take a final look at a very complicated network in the end here. But just to kind of set it up, we could have different units at different layers. So we have the concept units. Okay, so this one muddies the idea between input and output units a little bit. This is more of a sort of spreading activation representation of how we might store knowledge in our mind. So we have these concept units. Are we talking about pines? Are we talking about roses? Are we talking about robins? Are we talking about salmon? And then we have relation units. And these relations let us know if the relation between our concept and our property is a relation. So the top one there is a, that refers to this is a something else. So it's a category that it belongs to. Is a feature that the property that the concept has. Can is again a thing that the concept can do. So and then has are attributes that it actually has, that it actually possesses. So not things that it can do, such as is or sort of adjectives that it can be described as, but things that it actually has. So those are the nodes for the relation. These are the units for the property. So is it a living thing? Is it a plant? Is it an animal? Is it pretty? Is it tall? Is it living? Can it grow? Can it move? Can it swim? Does it have bark, petals, wings, feathers, right? So these are all the different properties that we're trying to represent. So these are, all the different properties here that we're trying to represent. So for these concepts, we're trying to form a connectionist network that can tell us which of these properties and which relations belong to these concepts over here. So in order to do this, we're going to need some representation and hidden units. So don't worry too much about the details of these. These are just to give us the necessary connections so that we can start representing all this information in our network. So let's start with a statement: canaries can grow. So if you know that canaries can grow, if somebody asked you, hey, can canaries grow? And you thought for a second and said, yes, they can. Canaries can absolutely grow. That means that you have that information represented somewhere in your mind. Maybe it's represented in this way. Maybe when you activate canary activates, when you activate canary and you activate can. So when somebody says canary and somebody says can, those two are activated. And when somebody says grow, that's activated as well. If those are true, then they should all be activated together. And one way to do that is to connect those through this representation node right here that connects to this hidden node right here that connects canary and the relation can together to that node. And then that node is connected to grow. So when somebody says canary can, that activates the idea of grow. So you represent canary can grow by the fact that canary and can are connected in such a way that they are both linked to grow. In a similar manner, canaries can move. So once again, we have the canary, we have can, and in this case, we want to connect it to move. So once again, that representation node gets turned on. Once again, that hidden node is connected to both the representation node and the relation node, and that is connected to the idea of move. So canary can move is now represented in this network. So another way to think about this is that if this is the only network you had, if this is the only connections you had in this network, you would know that a canary can grow, you would know that a canary can move, and you wouldn't know anything else about anybody else. All right, so this is very simplistic so far, but hopefully you can see how this knowledge could be represented. All right, so other things that a canary can do. A canary can fly. So as you continue to learn things about canaries, your network will update so that it can represent this information. So if you learn that canaries can fly, well, now your network has all of these connections in it. And when you learn that a canary can sing, now your network is going to add new connections, right? So this is also a model of how we might learn information, where we just continually update our connections, adding new connections to these previous connections. So when somebody says a canary can do what, that would activate a canary can grow, a canary can move, a canary can fly, and a canary can sing. And notice here that there's no connection to swim. So because swim is off, you would not think that a canary can swim, but you would think that a canary can grow, and a canary can move, and a canary can fly, and a canary can sing. So these connections here could be how you represent canaries. And then an interesting thing happens when you try to represent robin. So if you represent robin can, so we activate the robin node, we activate the can node, that robin node can connect to the same representation node. And that representation node and can still connect to the same hidden nodes. So once you learn about once you learn about canaries and you already have those connections in place, it makes it a whole lot easier to learn about robins. You can literally just kind of be like, you know what, a robin is like a canary. And then all of a sudden you just make those connections to the same representation and you go, oh, okay, a robin is like a canary? Well, I never knew anything about robins, but now that I know they're like canaries, I know they can grow, I know they can move, I know they can fly, I know they can sing, and importantly, I know they cannot swim. So you can piggyback your knowledge of robins onto what you already know about canaries, and again, build up that representation of your knowledge. All right, and now we'll take a look at is. So we looked at can. What about is? So we have Robin once again. We have the is relation activated. And then we want to activate this that a robin is living and a robin is red. So we have that possibility by linking the is to another hidden unit and then linking that representation that links Robin up to that other hidden unit. And then we have the outputs there to link to those property units. And once again, we are now representing that a robin is living. A robin is red. And then notice that this can get rather complicated because in this instance, we would have to try to put an activation for canary where canary does not activate is red, right? We want to activate canary is pretty. We want to activate canary is living, and we want to activate canary is yellow. So once again, we can go through this model and try to build up this information. We're going to want a new representation node activated because we can't just piggyback on what we know about robins. We need a new hidden node activated. And then that goes to the pretty unit, that goes to the living unit, and that goes to the yellow unit. So this is a very simple representation so far. We have literally just represented maybe 10 things about canaries and robins. And you can already see that this is kind of getting very complicated. So you can imagine how complex all the different connections in our minds must be in order to represent all the different things that we have in our minds, all the different knowledge that we have using these connectionist networks. So this is one of the reasons that connectionist networks really took off when computers and computer programming abilities kind of caught up with the idea of a connectionist network, because it is rather complicated. I mean, again, we're doing something super simple here, and I'm already starting to mentally lose track of, what are the connections and what are the implications here. So these connectionist networks, they're a model of how knowledge is represented. So this parallel distributed processing model says that the knowledge that you have is distributed in parallel across a wide variety of connections. So importantly, it's distributed. You don't have one node that says a canary can grow, but you have a pattern of activation that represents a canary can grow. And you don't have one unit or one node that says a canary is yellow, but you have a pattern of activation that indicates a canary is yellow. And you have a pattern of activation that indicates that a robin is red. And it's these patterns of activation that indicate the knowledge or represent the knowledge that you have. So that's the idea of distributed knowledge. It's not knowledge that's represented in a single unit. It's knowledge that's distributed across, in this case, multiple units, 1, 2, 3, 4, 5 units, in order to represent a robin is red. And in order to do real cognitive work, you need very big, huge, parallel distributed connectionist networks. So we're going to take a look at a video right now that's going to show us how this particular connectionist network can actually recognize numbers. And again, just keep in mind that these are the same connectionist networks that are leading to the increases or inability of driverless cars. These are the same connectionist networks that are allowing face recognition and so many of the advances, in our artificial intelligence technology. So let's take a look at how these connectionist networks operate. And importantly, we're going to take a look at how they're updated and how they learn. So this is also going to touch on how is it that these networks are created and they're programmed so that they can do these wonderful, wonderful things.
Step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random. Maybe something like 0.5, 0.8, 0.2, on and on.
Okay, so we'll start off. I'll just quickly mention something right here. So this right here on the right, this is the output that we want. So for this input of a 2, this input here is broken down pixel by pixel. Each of those pixels goes into an input unit here, and that activates the input unit. So if it's a white pixel, like that one right there, activates the unit. If it's a black pixel, does not activate the unit. The information gets spread throughout this entire network, activating units, sending excitatory connections, sending inhibitory connections, until the output comes over here. And the way that this output works is that whatever has the greatest activation, that's the number you recognize. That's what you think that this number is. So right now we have a connectionist network where we want the output to look like this. We want the output to be 0 is off, 1 is off, 2 is completely turned on, 3 is off, 4 is off, 5, 6, 7, 8, and 9 all off. What we get is we get this jumbled up output over here, where 3 is turned on and 6 is turned on. So this is designating confusion between 3 and 6. So this is a horrible output for this network, because not only did it not recognize this number as a 2, this network thinks that this number might be a 3 or it might be a 6. So it's not even guessing correctly at this point. So what do we do with this? Well, we update the connections using what they call backpropagation.
Now, we can't directly change those activations. We only have influence on the weights and biases. But it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU.
All right, so we're going to stop it there at the sigmoid squishification function, and basically just focus on the idea that the network gets things incorrect. And then what is done with this network is that for everything that's incorrect, it moves things closer to the correct output, and then uses a program, uses that very complicated function to change all of these weights here so that this stimulus gives us closer to this output and further away from this output. And this is how a connectionist model learns. And it learns through experience. So this is a very exciting thing because it learns much like we learn. We learn through experience. Connectionist networks learn through experience. So when you show this connectionist network, this number 2, and the connectionist network gives you the output that says, oh, that's either a 3 or a 6. What the computer programmers is actually doing is telling this connectionist network, no, that's not a 3, that's not a 6, it was actually a 2. And then you go on to the next training trial, and then you go on to the next training trial. And eventually, you will get to the point where if you present this network with a 2, the 2 will be activated the most, and the network will correctly recognize the number as a 2. If you show it a 9, the 9 will be activated the most, and the network will correctly recognize the number as a 9. And this is basically what we do in school, right? So think back to elementary school when you were learning your numbers, and the teacher would put up a number, and they would say, what number is this? And you might put up your hand, and you might say, oh, that's a 7. And the teacher said, no, that's actually a 2. This is a 2. Well, you would then update your own network, maybe in terms of how this connectionist network is updated. And over time, you would learn how to recognize 2s and 3s and 4s, and you would learn your numbers. So this is a connectionist network that will eventually be able to recognize numbers. And this is the concept between, or the procedure behind all of the new advances in artificial intelligence. So we have in this kind of self-driving car here, you have the self-driving sensors. This you can think of as an input unit. You have a forward-facing camera. This you can think of as an input unit. Radar senses. These are all input units. And these input units take in information from the external world, send it through a connectionist network that looks a lot like this, sends it through a connectionist network, and that connectionist network has an output layer to it. And that output layer, in this case, is outputs in terms of what should the car do. Should you press the accelerator? Should you press the brake? Should you turn left? Should you turn right? So these outputs are the outputs of what do you do to the car? What do you do? Should you turn on the turn signal? So all of these are possible outputs when you're driving a car. And there's a connectionist network that connects these input sensors, the self-driving sensors, the forward-facing camera, analyzes all those inputs, and then has the output unit that indicates what should you do to the steering wheel? What should you do to the accelerator? What should this program do to the brake? And the way that these cars are programmed, the way that these programs are made, is simply by allowing them to drive. And then if they make a mistake, if they end up crashing into another car, then you basically say, no, bad network. Let me update your connections so that you don't crash into a car. Let me update your connections so you don't turn off the road. And little bit by little bit, these programs are made so that they get better and better and better at self-driving. And then once you have a program that works, you can just copy it and make 1,000 self-driving cars. So these programs are very, very powerful. But again, they're all based on input units, hidden connections, hidden units, connections between them, and then output units that connect it to the external world by turning the steering wheel left, turning it right, accelerating, decelerating, whatever you need to do in order to drive a car. So we're going to end this look at connectionist networks with another example that kind of just shows you somewhere in between number recognition and self-driving cars, and that is how to play Super Mario World. So this is a very interesting kind of connectionist network that does nothing except learn how to play Super Mario World. So let's take a look at that right now. And again, we'll see how these connectionist networks can achieve very complicated behavior. And if any of you have ever played any of the Mario games, you will know that they can get very complicated. So let's see how this connectionist network handles that complexity.
Welcome back, Sethling here. You're watching a skilled player play Super Mario World, but this player is not human. It's a computer program I wrote called Mar.io. This program started out knowing absolutely nothing about Super Mario World or Super Nintendo's. In fact, it didn't even know that pressing right on the controller would make the player go towards the end of the level. It learned all of these things through a process called neuroevolution. In this video, I want to teach you about how Mar.io learned to beat this level, Donut Plains 1, what his brain looks like, and how it's all based on actual biological evolution. So let's start out by actually looking at Mar.io's brain. Let's play it again, but this time we'll look at Mar.io's brain as it's making the decisions of what buttons to press. It's going to look a bit complicated at first, but don't worry, I'll help break it down for you. This structure of colored lines and blinking boxes is called a neural network. It's a simple mathematical model for how a brain works, but it can produce some very complicated behavior. With enough computational power, a neural network could come close to simulating a real human brain, but modern technology isn't there yet. On the left side, you have the inputs. This is what Mar.io sees. It's a simplified view of the level. The white squares stand for blocks the player can stand on, and the black squares stand for moving objects like enemies or mushrooms. On the right side, you have the outputs. These are the 8 buttons that Mar.io is able to press by using its neural network. In between the inputs and the outputs, all those lines and boxes, those are the neural network. Each free-floating box is called a neuron, and the lines connecting those boxes are like the axons and dendrites in a human brain. At any given time, only some of these neurons and connections are actually being used, and this is what people talk about when they say you only use 10% of your brain. The neural network you're seeing is a pretty complicated one, and it got so complicated as a result of a 24-hour evolutionary learning session. So, to explain how neural networks work, let's rewind about 24 hours and look at how the whole process started. This is what Mario looked like at the beginning of its training session, all the way back in generation number 0. The program is probably even dumber than you thought at this point. Often it just stands there and doesn't even press any buttons. If Mario stands still for too long, it'll cut off the simulation and try the next neural network, so it's mostly just jumping from one simulation to the next. But occasionally, the neural network says suppress the right button, and the player starts walking right. The behavior isn't complicated, but it's enough to make at least some progress in the level. Let's take a look at a sample neural network to understand just how that works. This is one of the randomly generated neural networks that appeared in the first generation of the simulation. There are some green lines and a red line, and one neuron in the middle. Here's how it works. A green line is a positive connection, and a red line is a negative connection. A green line reading from a black or white square will turn its output the same color. A red line reading from a black or white square will turn its output the opposite color. In this case, the green lines read from the platform that the player is standing on and make the neural network press the right button as long as the player is standing on it. However, when the red line reads a black square representing one of those caped Koopas, it presses the A button and makes the player jump. This puts the player in a position where the green lines are no longer reading a white square, so the right button turns off and Mario just stands there. This is a really basic example that illustrates how a more complicated neural network might operate. The more lines and neurons you have, the more nuanced the decisions can be. So, how exactly do we get those more complicated neural networks? The answer is evolution. When Mario gets further right on the screen, its fitness goes up. In this case, fitness is a function of how far right it gets and how quickly it gets there. Only the neural networks that produce the highest fitness are selected to be bred, creating the next generation. It took 34 generations of genetic breeding and fitness evaluation before Mario was able to finish the level without dying and get a fitness score above 4,000. You can see there were several places it got stuck for a few generations, but it always evolved out of those ruts. Let's take a look at a few of those ruts. You can look at the top left corner of the screen to see what generation number each rut occurred on.
All right, so they're going to talk a little bit about the ruts right now. So the link to the video is in the lecture notes, so feel free to watch the rest of the video if you want to see how Mario got out of the ruts. But importantly for us, once again, this is a connectionist network that is able to achieve a very complicated behavior. And it's all made up of this box here is your input layer. This box here is your input units representing objects that cannot be moved and objects that are moving. And then it is linked to hidden units in the internal layers. And then those are linked to these output units that tell you whether you press button A, B, X, or Y. Do you press up? Do you press down? Do you press left? And do you press right? So that is the basic form of this connectionist network. And as you can see, it can play a video game in a very complicated cognitive feat. For those of us that game, we know that this is not something that comes naturally and is not simple, but eventually you learn it. And if you know how to beat a game, you have this connectionist network somewhere in your mind representing what should you do. Should you jump? Should you not jump? And that's possibly how we represent many of our skills. And that is how artificial intelligence is learning to play video games. And also, more importantly, in terms of application, for example, drive cars and recognize faces. All right, so that was the Connectionist Network, the world of Connectionist Networks.